right, thank you all for being here today. It's exciting to see all of these different fabric-based papers, and in particular, I want to kind of switch from thinking about the higher level interfaces that are enabling us to create all sorts of interesting interactive materials with knitted objects or with other textiles, and get down to the really basic level of operating these machines. Amongst the research that we've seen here today, there's a lot of focus on UIST and the wider HCI community on advancing what we can do with textiles, and we've seen all sorts of advances over the past few years in automatic machine knitting, as well as creating e-textiles with automatic knitting. And this comes from the very basic sense that we can just form knitted structures by pulling loops through other loops. So if we imagine we have this white loop of yarn here, and we pull on either end, we just get a fiber taut. But if we put another loop through it, we've created a structure that is stable, so that that white loop is now able to kind of pull against the gray loop. And if we expand on this, we can create all sorts of interesting and controllable physical properties and embed them into our fabrics. And we can also represent these different textures and metamaterials as a graph structure, which I call knit graphs. There's a variety of different versions of knit graphs. They're all expressing some relationship between the yarns, the green arrows here, and the stitches, the purple arrows that are connecting those different loops. And I particularly want to call out the work by Jenny Lin and Jin McCann on art and braid groups, which take this idea of a knit graph a little bit further, allowing us to represent the arrangement of those loops, not just how they're connected to each other in a wale or in a series of stitches, but as how they are kind of overlapping on top of each other. Now, there's a lot of interesting things we can do with this knit graph structure. We can think about that as kind of a medium for design. But the thing that always kind of sticks with me is a deep fascination in the machine itself. Oh, the videos aren't playing. There we go. I like to think of this as a symphony of needles and yarns orchestrated by carriage passes. And I'm going to go into more detail about what these operations are. So for when we're doing machine knitting, we have a set of front and back bed needles. These are aligned, and we can create different stitches on each of them. And we do that by using a carriage, which actuates and moves across these needles in a leftward or rightward direction. In that case, moving over to the right side. The yarn is brought in on yarn carriers, which provide the yarn that's going to form the different stitches. And so we can go across and create loops on each of these front bed needles using what we call a tuck instruction, which is just going to place a new loop onto a needle, even if there are other loops already there. We can also do this with knits, but that's going to pull a new loop through the loops that were already on that needle. And so we can do this by then combining knits and tucks to form a fabric made up of different stitches. Now, it's not that interesting to keep all of these stitches in one place, and so we have transfer operations which allow us to move loops from the front to the back bed. So in this case, we can rearrange the stitches to change the texture of the fabric, creating different knits and purl structures. And we can take that even further by racking or realigning the front and back beds so that when we make those transfers, we can do things like create eyelet increases, where we move one to the back bed and then back over to create a new space. Or we can create decreases, where we take a loop and shift it over onto another loop to be stitched through later. Now, last year I presented KnitScript, which was a new scripting language, a programming language for knitting machines. My goal is that this is a system that all of you can use to get into the knitting space and more quickly develop in the knitting on top of the knitting infrastructure. This is a challenging space to get into, and so I wanted to create a language that was more supportive of learning about machine knitting. So for example, we can have structures, we can write code like this very simple code that's going to knit back and forth and create different transfer operations for us in an intuitive way. Now the problem with KnitScript, though, is that not every intuitive knitting algorithm is going to be efficient. Especially if you have a hand knitter, you might have the intuition that you will transfer loops onto your decreases and then knit through them. And this creates these really inefficient knit structures. So you can see here the yellow yarn is being moved to the back and then back over to the front, and then we're knitting across it. If we slow that down and look at this kind of stitch by stitch or operation by operation structure, we get this kind of diagonal pattern. And what I want to highlight here is that this is going to create one linear row of cables, or a complex structure like the ones that Hannah was talking about earlier. And all of that black space is wasted machine time. Not just wasting time on the machine, which may be on an order of magnitude of something of a sweater, many minutes or hours, but also a lot of wear and tear on the yarn. Every yarn is being moved here and racked back and forth, causing the fabrication process to be less reliable. And so that's where KODA comes in. Knit program optimization by dependency analysis. The basic idea behind KODA is that it's here to consolidate carriage passes, to turn what was one kind of diagonal structure of creating different cables into this consolidated process where we're knitting all of them together in this linear way. And so now we can consolidate into this kind of fast row-by-row knitting without without changing the kind of intuitive algorithmic structure that we use to create it. So in this case, in the same amount of time, we're able to make 7 rows of cables. Now, I'm going to walk you through a very trivial example to show you what dependency analysis is and how we create these different structures. We have 2 graphs now. We've got the knit graph, which represents the physical structure we're being knit, but we also have a dependency graph, which is the relationship between the different operations in the order that we knit them. So for instance, I might go across and knit the first 4 stitches of my needle, and I now have yarn order dependencies between them. This says that I can't knit the second loop of my structure until I've knit the first loop of my structure, because I have to have the yarn pass between them. I can then go and transfer in that intuitive way, setting myself up to make a purl stitch, and this creates a loop position dependency. Anytime I'm going to knit through that 4th loop now, I'm going to have followed the dependency that I already did this transfer, because otherwise it won't be there when I need to knit it. Then I move the carriage back, and I can knit the 5th and 6th stitch, creating this knit purl pattern in a standard rib structure. And now we can see stitch dependencies forming between the loops of that we had knit on the original row and the knitted stitches that we're creating, as well as that transfer operation. I can then repeat this process to intuitively prepare my stitch for the next purl on number 2, and then knit across all of them, creating my nice rib pattern. Once we have this dependency graph, which we can create in a linear way, just kind of running through all that program, we can start to notice different carriage passes, those lines of different operations that are all conducted in a single pass of the machine. So we've got that first set of tucks that are putting all of our loops together, and then we've got a second and third carriage pass to add this transfer operation and this set of knits. And then finally, we have our 4th and our 5th carriage pass to do the next transfer operation and the subsequent knits. But if we think about this dependency graph instead of being a strict ordering that we followed from the original program, instead of topological ordering, we can find that there are layers of this graph structure which reveal opportunities to consolidate the transferred stitches. And so here we can see that the topological ordering allows us to put the 2nd and 4th transfer, or the 1st and 2nd transfer, into the same location, into the same pass, and then we can complete the operations on the knitting all in one pass, reducing ourselves down to 3 carriage passes. Now, 2 carriage passes is probably not that important in terms of timing, but when you're talking about creating these structures over very large pieces of fabric with many thousands of stitches, you're going to really reduce your time if you started with something that was an intuitive algorithm, but one that did not work well. And so we can optimize to free up the complexity for knit programmers. We can think about what just makes sense for us, what makes sense for us as programmers, without really regarding the machine level operations and how efficiently we're arranging our transfers. My goal is that KODA is a useful tool for knit developers alongside KnitScript to help us focus on creating intuitive and understandable knitting algorithms, to reuse code, not only for ourselves, but to borrow code from our colleagues and people who are creating other kinds of knitting algorithms without kind of regarding how this affects machine level efficiency. Maybe they're not very compatible algorithms in terms of how they handle transfers, but KODA will take care of that for you on the back end. KODA ensures that you're going to produce the semantically correct program, so your optimized program will be guaranteed to produce the same knit structure. It just does it in a more efficient way. So what you knit will be what you knit. And then KODA uses a greedy method to reduce the carriage passes. So this doesn't ensure that you've got the globally optimum or efficient program, but in the worst case, it's still going to be as efficient as your original program. And in many cases, it can reduce it by significant amounts, which we demonstrate in the paper. Ultimately, my goal is that we can take tools like knit-out, which is kind of the base language that I showed you earlier for each of these individual operations, the higher level scripting language like knitscript, and systems like KODA that enable more efficient development of CAD tools to bring about a new future of knitting CAD. And with that in mind, I want to thank you all and ask if there are any questions.
If you have a question, feel free to come up to the mic. One question that I had to start is for the equivalence, like if it has a similar or an equivalent topological structure, could that affect like the tension in the yarn or how elastic it is in the final pattern, or is that also equivalent?
So it will produce the exact same topology of the knit graph, and so it shouldn't affect any of those features. I've only shown in the talk yarn order dependencies and loop position dependencies, but we have a variety of dependencies that we analyze out of the knit graph structure in the paper. So there's more details about how we manage those kind of operations to ensure that you're not changing any of the physical properties of your final knit structure.
Hi, this is Yuhao Zhu from Rochester. This is incredibly cool, especially for someone coming from the programming language background. And I'm completely uncalibrated here, so my questions might not make sense. But I was just curious how much of this depends on the actual knitting machine. It's like, you know, if you think of an actual computer program running on an actual computer piece of actual computer hardware, you know, different hardware architectures might have different assembly languages. And so, you know, that's sort of the lowest level primitive instructions that a typical computer program works with. So I'm assuming that different knitting machines might have different primitive like operations, and do you kind of have to somehow then compile your program, optimized program to different kind of optimized versions of the assembly programs, depending on the knitting machines?
Yeah, this is a great question. So there are different operations and different types of knitting machines. The kind of knitting machine I'm showing here is called a V-bed knitting machine, so that's why it's got the front and the back bed. And the set of operations that we support are pretty universal to that style of machine. You'd be making very different knitted structures on other types of machines. But we did think about this in the development of it. So we wanted to make sure that the way that we build the dependency analysis as we process the knit graph and run through the instructions, there's a modular set of structures in the library so that you can add new types of dependencies. And so if you were to redevelop this concept for a different type of machine on a slightly different version of the knit-out language, you could identify different dependencies that are maybe unique to that machine and embed them into the system. And so that process doesn't change too much, or building different versions of KODA for different firmware is going to be pretty trivial.
Okay, so dependencies are defined with respect to a particular knitting machine, I guess.
Exactly.
Okay, all right, thanks.
Awesome. Thank you for that question. All right.